Okay, so the final thing that I want to talk about for this chapter. Oh, and look, chapter 16, guys, it has capacitors in it, but I'm not going to teach you capacitors until we do circuitry, which is chapters 17 and 18. Okay, so it's not in the homework set. It'll be in the chapter 18 homework set. So the final topic for this chapter is equipotential surfaces. Equa referring to equal, potential referring to electric potential. So check it out. Here I have a big dude, this big positive charge, and let's travel a distance r from this big guy, right? This is big guy, capital Q. He is a big Q. So if you travel a distance r from the big guy, from the point charge, you can calculate a few things. So from chapter 16, we learned that you could calculate the electric potential. Capital V is electric potential, and the equation for that is K Q over R. Now from last chapter, when we did electric fields, you could calculate at this point right here the electric field. K Q, absolute value on the Q, over R squared. In the electric potential equation, Q is not absolute valued, but in the electric field equation it is. So I've been saying all week, which one of these is more of a pain in the butt? Electric fields or electric potential? Electric fields are more of a pain in the butt because they are vector, they have direction. You know, so if you have multiple electric fields, you got to put them tip to tail. You know, the resultant electric field goes from the tail of the first to the tip of the last. It's a lot more work. The nice thing about electric potential is that it's scalar. Okay, so if you have multiple charges and you want to find the electric potential at a point, just add it up and make sure if one of the charges is negative, you got to plug it in as negative. Q is not absolute valued. Okay, so what's this whole idea with equipotential? So look, so I went to a point R. I went to a point that's a distance r from the charge. Well, let's go to another point. Ready? Distance r, same exact distance. So these 2 points right here, if you look at the equation for electric potential, the charge is the same, right? We're going away from the same charge, and r is the same, and k is a constant. So what does that tell us about these 2 points right here? These 2 points would have the same electric potential. Do you guys get it? Okay, let's go to a third one just to be super duper clear. R, right there. That point, same Q, same R, the electric potential would be the same. So every single point on this circle is at the same electric potential. Does that make sense? So we call it an equipotential surface. Now, trick question. I want you to be on your A game here. Would these 3 points have the same electric field? Would the electric field be the same? Well, look, Q is the same, R is the same, K is the same. So you'd be like, oh yeah, man, these 3 points right here have the same electric field. Wrong. Remember I told you electric fields are a pain in the butt? Why would the electric fields technically, I mean, the value, the magnitude would be the same. When you plug into here, you're going to get the same answer for all 3 points. But why would they be different electric fields? Because direction. Right here, the electric field's going that way. Right here, the electric field's going that way. That way. Electric fields are vector, dude. They are vector. Okay, now here's a problem that's going to kind of give you an idea of how you would see this. So I just made this up. So we have a proton released from rest at point A. So here's point A. So we stick a proton right here. Oh, look, and this problem assumes that we have proton info. Charge of a proton, 1.6. Mass of a proton, 1.67 times 10 to the negative 27. Okay, so we put this proton right here at point A and release it from rest. What's that proton going to do? It's going to go boo. It's going to accelerate towards point B in the same way that a mass would accelerate down the gravitational field, right? So we're going to find we want to find out what's the kinetic energy at point B, okay? So the equation we're going to use is this. Potential difference, V is not velocity here, V is potential. Potential difference is defined as change of potential energy per charge. All right, so rearrange this. Change of potential energy is going to be delta V times Q. Now, which Q are we talking about here? Are we talking about the big Q or the little q? It's the little q. It's the charge that's experiencing the change of potential energy. All right, so change of potential energy. Now, what is our delta V? Well, point A, check it out here. Point A is at 100 volts. Point B is at 30 volts. Hey, man, and notice that the volts get smaller as you move that way. You should understand why. V equals KQ over R. As R gets bigger, V gets smaller. Okay, so what's the difference between 100 and 30? Negative 70, right? Because we're starting at 100 and ending at 30. If you start with $100 and end with 30, I think you would agree that your change was negative. Okay, so negative 70. A volt is a joule per coulomb. The proton is 1.6 times 10 to the negative 19 coulombs. So our change of potential energy for this situation is going to be negative 1.12 times 10 to the negative 17 joules. So that's our loss of potential energy. So what's the gain of kinetic? Same number, but what? Positive 1.12 times 10 to the negative 17 joules. Okay, then for the second question, what's the velocity when the proton reaches point B? So how do we do that? We use the kinetic energy equation. So kinetic energy equals 1/2 mv squared. Ooh, this V now, is that electric potential? No, now it's velocity. So velocity is going to be square root 2 times kinetic energy over m. So take your m, plug it in, take kinetic energy, plug it in, and oh dude, I forgot what this is. Hold on. So that is, oh, I got it right here. 1.16. So it's basically, we'll just call it 116,000 meters per second. I'm pretty sure that's what it is. All right, you get the concept? Equipotential surfaces. This is how you'll see it in problems. They'll give you the electric potential on this circle. They'll give you the electric potential on that circle. Then they'll ask you a question about moving a charge from one circle to the next.